Suppose I have a positive fixed charge sitting in space, fixed meaning it cannot move, and I have another positive charge that we'll call Q2 that is approaching Q1 with some velocity. Then we know that since both are positive, Q1 is going to repel Q2 in the opposite direction, so Q2 is going to accelerate to the right while it's moving to the left, and so it's going to slow down and eventually turn around, where at this point it has velocity 0. And our question is, what is the minimum distance that is achieved between Q1 and Q2? The minimum distance. So this scenario is very similar to the concept you have in projectile motion, where you're trying to find the maximum displacement of your projectile. But in this case, instead of finding a maximum, we're trying to find a minimum. In both cases, we can resort to the idea of potential energy. In this case, it's going to be electrical potential energy, which should not be confused with electrical potential, which is a different concept for the next video. So for now, we're going to consider systems of two charges. Systems of two charges. You can have systems of multiple charges, and we'll cover that in a next or in a future video. But for now, we're going to be grounded for two charges. So if we have this system, and we'll suppose both charges are stationary for now, and we call this distance between them r, then the electrical potential energy held within the system is given by EE equals K Q1 Q2 divided by R, where K is Coulomb's constant, so K equals 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Q1 and Q2 are the values of both charges, and R is the separation. Now for this electrical potential energy, you'll notice it's very similar to the force equation, except now we're dividing by R instead of R squared. And the second difference is that this is a scalar quantity. Scalar. So there's no direction. With that being said, you can still have positive and negative values, and so there's two cases that we need to identify. So we have case 1, where we have like charges. So we either have two positives or we have two negatives. And if we draw this out, we have two negatives or we have two positives. Then we know that since they're both like charged, they will repel each other. And after some amount of time, they're going to accelerate in opposite directions and have velocities in opposite directions. So in each case, they will have some velocities after some amount of time. What this means is after some amount of time, they will have some kinetic energy. Each system will have some kinetic energy. And these systems are isolated, so the negatives and positives do not attract each other. So after some amount of time, they will have some kinetic energy. This kinetic energy had to have come from somewhere, because we know energy is conserved, and the place it comes from is the initial electrical potential energy at the beginning. And so what this tells us is the electrical potential energy at the beginning had to have been greater than 0 in the case of like charges. So if the charges are like, then the electrical potential energy held in the system is positive. Now the second case, case 2, is when it's opposite charges. So we have a positive and a negative. If we consider the simple case, where we have a negative charge and a positive charge sitting right beside each other, then if we look at the system, nothing is going to happen, because both charges are going to attract each other, and so they're going to be stuck. They're bounded together. If we separate them by some distance r, or some distance r1 rather, We'll call that R1. And we do the same thing, but instead we'll separate them by a distance R2, where R2 is greater than R1. Then they're going to attract each other. But in the second example, they're going to travel for a longer distance to reach the middle, which is the equilibrium position. That's where they want to go to, and then they will stay stuck together. So they want to accelerate towards this equilibrium position, but in the second example, they will accelerate for a longer amount of time. And so they're going to reach some velocity v2, and they're going to reach some velocity v1 right before they make contact. And since they're traveling for a longer distance and a longer amount of time in the second scenario, then v2 is greater than v1, and so the kinetic energy in the second system is greater than the kinetic energy in the first system. But the distance in the second system is larger than the distance in the first system. So what we conclude is the larger the distance, the more energy for opposite charges. But if we look at our equation, it's proportional to the reciprocal of r, or 1 over r. And so the larger the distance, the less the magnitude of potential energy. But we said that the actual amount of energy has to be greater. And so, in this case, the electrical potential energy is negative, because if we look, the magnitude of a number, so we'll say 3, is less than the magnitude of a larger number, so 5. But if we compare their negatives, negative 3 is larger than negative 5. And so for this all to make sense, the potential energy in a case where the charges are both negative, or they're oppositely charged, so positive and negative, the electrical potential energy has to be less than 0. And another way to think about it is if we have our negative charge and our positive charge stuck together, then the only way I can get them moving and add velocity to both charges is if I apply a force. So a force that is applied by me. So I will do work on the system. I will add energy to the system to get the charges to move, or to get them separated. And so if I'm adding energy such that the kinetic energy can increase, then the system must have had a deficit of energy, and so the system had to have had energy that is negative. And if you don't want to memorize this, if you look at the equation, then if both charges are opposite, so positive and negative, then multiplying these together, you will get a negative answer. And if both charges are alike, so positive and positive, you'll get a positive answer. And if both charges are negative, you will get a positive answer. And so even if you simply plug in the values, you'll get the same result. Now there's one last thing we need to talk about for the electrical potential energy, and that is that it's since the electrical force is conservative, so the electrical force then essentially what we have is, if we have two positions, A and B, and we take a path that we'll call A, from A to B, and we take another path from A to B, which we'll call B, then the change in energy, delta EA, which is the change in energy for this path, and we have delta EB, which is the change in energy for the second path. Since the electrical force is conservative, the change in energy for both paths is going to be the exact same. They will be equal to each other. So essentially what we have is that the change in energy for the electrical force does not depend on path. So all we have to do is delta E is equal to the energy. I'll write this in a different color to make it more clear. Delta E is going to be the energy at the final state, which is B, minus the energy at the initial state, which is A. And with that out of the way, we can now proceed to an example. So we have a small sphere of mass 25 grams and charge 20 microcoulombs that is attached to a string of length 1.2 meters to form a pendulum. We place this system within a downwards uniform electric field of 5 times 10 to the 3 newtons per coulomb. And we want to know, if we drop the pendulum from an angle of 3 degrees, what is the maximum speed it attains. So if we consider our system, we have a string of length 1.2 meters, a mass of 25 grams, and charge 20 microcoulombs. It's being dropped from an initial angle of 30 degrees in an electric field that's going downwards of 5 times 10 to the 3 newtons per coulomb. And we want to know the maximum speed it attains. Well, if we consider the free body diagram of our mass, it's subject to the gravitational force going down. And since it's positively charged and the electrical field is going downwards, the electrical force is also going downwards, and so its net acceleration is always going to be downwards. In the first case, it's going to be traveling downwards, and so it's going to be speeding up because it's moving and accelerating in the same direction. And in the second half, it's going to be moving upwards, but still accelerating downwards, and so it's slowing down. And so the maximum speed is right in the middle, or the equilibrium position of the pendulum, and that's where the velocity is at a maximum. To actually solve for the value of this maximum velocity, we can consider the conservation of energy. So ET1 is equal to ET2, where our first state is going to be right before we drop the pendulum, and our second state is where we want to find the maximum velocity. They're the same thing as saying the initial gravitational potential energy plus the initial electrical potential energy plus the initial kinetic energy is equal to EG2 plus EE2 plus EK2. And then we can move everything to the right side. So we have 0. We'll have EG2 minus EG1, which is the change in the gravitational potential energy, plus EE2 minus EE1, which is the change in the electrical potential energy, plus EK2 minus EK1, which is the change in the kinetic energy. So if we consider the change in the gravitational potential energy, this is equal to EG2 minus EG1, which is equal to mg h2 minus mg h1. And since we only care about the change, what we'll do is we'll call this, because we don't know how high this contraption is, this could be the ground, This could be the ground, we don't know. So we'll call the bottom of this curve our reference point, where H2 is equal to 0. And so this value is equal to 0, and our change in the gravitational potential energy is equal to negative mg h1, where this is now h1. And you can see that that means the change in the gravitational potential energy is negative, which makes sense because we're going from a higher position to a lower position. And this also means that we have a transformation of gravitational potential energy to kinetic energy, which is why we expect the kinetic energy to go up and the speed to go up. Now, the change in the electrical energy is equal to, well, we said in the previous slide that this is equal to K Q1 Q2 over R. So this would be equal to delta R. The only problem is that we do not have both charges. We only have one charge, but we're given the electrical field. So what we can do is that we know that the force, or the work rather, is equal to the change in energy, which is equal to the force times the displacement. The force in this case is the electrical force, and the displacement is position 2 minus position 1. We know that the electrical field is equal to the force per charge, and the charge we have in this case, we'll call it Q1. And so Fe, the actual force, is equal to the field times the charge. Our d2 minus d1 is the same thing as h2 minus h1. They both refer to positions. So this is equal to h2 minus h1. But we just said that h2 is going to be our reference. It's going to be equal to 0. And so our delta EE is equal to negative EQ H1, where again H1 is the separation between our reference and the initial position. And again, it's going to be a decrease, which makes sense because your force is downwards. And so starting at this position, you will be pushed away, lose energy, and speed up. Finally, we have our change in the kinetic energy, which is equal to EK2 minus EK1, which is equal, since EK1 is 0, because we're going to be dropping from rest, so EK1 is 0, so our change in the kinetic energy is simply equal to EK2. And now we're ready to sub all of this in. So just as a summary, we have our equation. Now the change in the gravitational potential energy is negative mg h1. The change in the electrical potential energy is negative EQ h1. And the change in the kinetic energy is positive EK2. So we can reorganize it. We have 1/2 mv squared, where v is our maximum velocity, or maximum speed, is equal to, since we have positive EK2, we'll move these two guys to the left side. So we have mg h1 plus EQ h1, and they're positive because we moved them to the other side. Now we can factor out h1 since it's shared between both. So this is equal to h1 times mg plus EQ. And if we want to isolate for velocity, we can say that the velocity is equal to 2 times h1 divided by m times mg plus EQ, all square rooted, and since the speed has to be positive, we take the positive root. Now the only thing we need to figure out is what h1 is. So if we consider our pendulum once again, it's going to travel like this. This is our reference, and this is our initial height. Then H1, this is also L. H1 is going to be L minus this distance. And this forms a triangle with angle theta over here, which is 30 degrees. So H1 is equal to L, which is the entire left side, minus the blue portion, which is the adjacent side of our triangle, or L cos theta, and we can factor out L. We get H1 is equal to L, 1 minus cos theta. And so your velocity, if you plug in, your maximum velocity is equal to 2 times L, 1 minus cos theta, all divided by m, times mg plus eq square root. I'll erase this to get more room for when we actually substitute. So Vmax is equal to the positive square root of 2 times L, which is 1.2 meters, times 1 minus cosine of 30 degrees, divided by m, which is 25 grams, but we want everything in SI units, so it's 25 times 10 to the negative 3 kilograms, multiplied by the same thing for m, 25 times 10 to the negative 3 kilograms, times g, which is 9.81 newtons per kilograms. I'm running out of room, so I'm going to move to the next line. Plus E, which is 5 times 10 to the 3 newtons per coulomb, times our charge, which is 20 microcoulombs, but again we want SI units, so it's 20 times 10 to the negative 6 coulombs. All of this square rooted. And if you plug that into your calculator, you will get a final answer of 2.11 meters per second. And let's work out our units. So we have over here meters per kilogram. This 1 minus cos 30 doesn't have any units. These kilograms will cancel, and these coulombs will cancel. So this is newtons over here. So essentially we have the square root of meters per kilogram times newtons. But our newtons are kilogram meters per second squared. So meters per kilogram, kilogram meters per second squared. So then these kilograms cancel out, and we get the square root of meters squared per second squared, which is meters per second. And that's your final answer. 2.11 meters per second is the maximum speed attained by the pendulum.